Good afternoon, professors. Welcome for the third session of FTTP. So we have our resource person, Dr. Usha Devi ji, ma'am, Associate Professor and Head, Information Technology, School of Information Technology Engineering, Institute of Technology, Chennai. Her areas of specialization are networks, security, machine learning, and IoT. She has published more than 54 papers in international journals and conferences. And I welcome you, ma'am, for this FTTP.
Yeah, thank you, ma'am. Is the screen visible?
This is all yours, ma'am. You can start your session, ma'am.
Yes. Is the screen visible, ma'am?
Yes, ma'am. It is visible, ma'am.
Okay, ma'am. Yeah, good afternoon, everyone. Am I audible?
Yes, ma'am. You're audible, ma'am.
Okay. Yeah. Yeah, this session is for applications of graphs. So please be interactive. And then, so if you have any questions in the middle, and then you may ask, and then so. Okay. So graph is for two components, two major components. One is for representing the vertices. Okay, and then so all these circles and then specifies vertices, and then there should be a connectivity between one vertex to another vertex, which is called as an edge. Okay, so this is for expressing the relationship between two different items or some pair of items, and then that's why, and then so we are going to make use of these graphs, and then so actually it can also be called it as networks. Then so usually what we have in case of networks, and then it has some connection of components. Okay, so these are all these vertices can be called as a components, and then there should be some interaction between one component to another component. Okay, that should be done with the help of a connecting line. Okay, so for example here 0, which is one of the component. Similarly, one is also another component. Now we want to pass some information from one to another. In order to do that, and then we have a edge. This is a connecting line. So therefore, and then if something is happening here, and then that information has to be passed it from, okay, this component to this component. For that, and then we are making use of edge here. In case of graphs, and then we can call it as vertices and edges. In case of networks, and then so it can be called as, and then nodes, and then maybe lines or connection lines or wires or some kind of cables. Okay, and then so depends on the terminology we are going to interpret. Okay, that's all. And then so generally, and then it should be coming from graph alone. And then so it has two components. What are those things? Vertices and edges. Okay, and then so all these vertices should be named, and then either it should be numbered or named, and then in order to uniquely identify the concerned vertices. And then so since, and then so if you have so many vertices, and then from where to where, and then you are trying to connect it, and then therefore in order to differentiate that, and then we can have a naming process. Now this is a numbered graph. Then the numbered components are from 0 to 4, and then so totally how many number of vertices are there? How many vertices are here? Yes, answer please. Am I audible?
N minus 1.
Ma'am, you are audible, ma'am.
Okay, okay. Yes, but there is no response, and then that's why I have a doubt. Hmm. How many vertices are here?
7.
7.
Sorry, ma'am. 5 vertices, 7 edges, ma'am.
Okay. So 0 is the first vertex, 7, sorry, 1 is the second one, and then 2 is the next vertex, and then 3 is the another vertex, and then 4. So totally we have 5 vertices, and then these 5 vertices can be connected in some fashion, and then so depends on how you are going to, okay, communicate, or how you want to, from where to where, and then you want to pass the information. Based on that, the connectivity has to be made, and then that is called as an edge. So in this case, and then from 0 to 1, there should be some communication. It means that we are passing some information from 0 to 1. Similarly, from 1 to 2, and then 2 to 3, and then 3 to 4, and then from again, okay, so 4 to 0, again 4 and 1, and then those are connected. And then so totally, and then how many edges we have? How many edges? Yes. 7 edges. Okay, and then so then this is one of the simple graph, and then have seen, and then so then you can define a different graphs, and then okay, so that one is, first one is called as a directed graph. Then the second one is an undirected graph, and then so there should be direction which is mentioned. Then okay, sometimes, and then it is not mentioned. Based on that, and then we have two types. One is directed, another one is an undirected. Then so this graph is which, under which category? Directed or undirected?
Ma'am, undirected, ma'am.
Undirected. There is no direction mentioned. Simply it is connected with k 0 to 1 alone. And then so it means that, and then you can transfer anything from 0 to 1 as well as from 1 to 0. Both the ways are possible. In such case, and then so we are going to mention it as undirected. Okay, and then so suppose if you want to pass anything from only one way, 0 to 1 alone. So you need to mention the direction. Arrow has to be, okay, put it here, and then suppose from 1 to 0, then this side arrow has to be mentioned, and then okay, that is called as directed graph. And then so these are the basic differences. So we will formally, and then we can express, and then how do you represent directed as well as undirected graphs. Then I'll start with the directed graph, so which is also called as digraph. Okay, it means that directed graph. All the graphs, and then has to be expressed in terms of, okay, these two parameter. One is set of vertices, okay, in case of networks, and then we can call it as nodes. And then another one is edges. So these edges, we can also call it as arcs. Okay, and then so these are the two different parameters in order to form a graph. And then, okay, that overall we can express it as G. Okay, so this is a mathematical notation for it. G is a graph. It contains two components. One is set of vertices, another one is set of edges. Okay, and then all these edges has to be specified with the direction. So therefore, it should have only set of edges alone. Okay, and then so it may have a connection from one vertices to another vertices. That's why, and then you may have at the maximum of kv into v. For example, so if the number of vertices are 3 means 3 into 3 combination, you can have the directed edges. Okay, and then so that should be the subset of this arc. Okay, so A is an arc, and then so that is a subset of V into V, number of or set of directed edges that is mentioned here. Then similarly, the arc is, how do you mention the arc? And then so which is called as an E. Okay, so E is an edge here, and then there should be a connectivity from U to V. Okay, so since it is directed always, and then okay, the from is going to mention first, and then to. Okay, where to you are going to pass the information that is mentioned in the next one. So these are the two pair, and then this should be only the ordered pair. You should not change it, interchange it. So in that case, and then the direction goes off on them. So each arc should have an ordered pair that is represented mathematically like this. So E is equal to U comma V. Okay, so therefore a digraph can have, okay, so looping also. From U to U, you may have a connectivity, that is edges. Okay, can also from the same vertices to another, the same vertex also you can have a connection. Okay, so that is called as self looping. Okay, and then so if the pair is from U to U, then which is called as self loop. Then always, and then the director graph has to be represented with the relationship asymmetric. What does it mean? Asymmetric? Asymmetric relationships. Anyone can answer. So this is also one of the important property in the directed graph. It should be represented with asymmetric relationship alone. In case of undirected graphs, and then so those are having symmetric relationships. What do you mean by a relationship? We should have a connectivity. Some information can be passed from one to another. So those pair are having certain relationship. Okay, and then so that relationship should be mentioned as asymmetric. Okay, and then so in that case, okay, so no need to maintain the written one. For example, in case of networks, we are saying that, and then I am passing all my data from one to, that is source to a receiver. But sometimes I may get an acknowledgement back. Those acknowledgement should not pass the same path itself. Okay, so that comes under asymmetric relationship. Sometimes, and then so I may use a sing one path for, okay, yeah, outgoing, and then similarly another path for, okay, incoming. Okay, and then so that maintains asymmetric relationship. If you are trying to use the common path for both incoming as well as outgoing, then that comes under symmetric relationship. Okay, symmetric path. And then so always, and then directed graphs, and then uses asymmetric. Okay, and then so no need to come back again. And then these are some of the examples of directed graph. And then so this direction is very important. It means that always the flow of data from, okay, so this vertex to this one alone. Sometimes, and then you may have bidirectional. Okay, and then so what does it mean? The both the ways are possible. Okay, so from here to there, as well as from, okay, so this vertex to this vertex, and then the information can be transferred. Okay, you are trying to connect, okay, from one to another, and then so the direction alone, the information flow has to be represented like this, okay, with the help of arrows, and then okay, so this is a unidirectional flow, and then this one is a bidirectional flow. Okay, and then this is one of the example of directed graph, and then similarly this is another kind, and then you may also have a, okay, what is this, and then so this is a bidirectional, and then this one is two unidirections. Okay, from 2 to 4, you have to make use of this path. Then from 4 to 2, and then you can make use of this path, and then okay, so that's why, and then okay, we are trying to use a different path for okay 2 and 4 communications. Okay, and then then we'll come to the undirected graphs. Then similar to directed graph, and then we are going to mathematically represent, okay, with g is equal to v comma e, and then so v is set of vertices, and then e is the edge, and then okay, and then in case of the set of edges, okay, so it should be minimal than we are undirected, sorry, directed graphs, and then okay, so this is a capital E that contains some set of edges, then that should fall under, okay, what is this, v2, okay, it's a combination, okay, and then then therefore it should be minimal than directed graphs, then okay, and then here it is an unordered pair, and then okay, either you can have u comma v or v comma u, and then so both the things are possible since it is, since there is no direction. Okay, and then so therefore both the ways are possible. That's why, and then it comes under unordered pair, and then okay, and then then it should not have any self loops, since what will happen, and then there is no direction specified. Okay, and then then it should have only symmetric relationships. Okay, and then these graphs represent symmetric relationship. What does it mean? Then the same path could be used for reverse communication also. Okay, and then no need to go for a new path, and then instead of that, and then okay, so which is used for the incoming, okay, transfer, the same path could be used for outgoing transfer also. Then these are some of the examples of undirected graph. Okay, just see here. Then there are 4 vertices, and then these are connected in some fashion. Then all these are edges. Okay, and then from here to there, and then you may use this path, and then similarly from here to there, and then either this or this. Okay, so multiple paths can be possible in case of undirected, and then okay, similarly 6 vertices undirected graphs are mentioned, then it is having totally 9 different edges. If you want to transfer anything from 1 to 6, there are so many paths available. Okay, so which is at present free, you can make use of it, and then sometimes you are trying to use the shortest path, and then or best feasible path or optimized path, and then okay, so that's for, and then easy transfer or okay, effective transfer, and then therefore in case of undirected graphs, and then you may have multiple paths, even one path is failed, and then you can make use of another path, and then and then that time, and then it will help you a lot, and then so these are the introduction about a graph. Now we'll move on to the applications. Yeah, there are lots of applications can make use of graphs. One of the most important or real-time application as social networks, and then everyone involved in a social network, there are Twitters, Facebook, etc. All those things are there.
Ma'am,
Yes.
ma'am, sorry to interrupt. The slide is not moving. Yeah. Now fine. Ma'am. Yes. Ma'am.
Oh, in case of full screen, and then it's not visible. Yeah, these are the slides. Now is it movable?
Yes, yes, ma'am. Yes, ma'am. Thank you.
Okay. Okay. Mm. In case of full screen, and then it is not visible, I think so. Okay. Mm. Yeah. There are lots of applications involve graphs, and then so one of the most important real-time application is our social network graphs. Then just see here, and then so many users are involved worldwide, and then so then there should be a connectivity from one to another. Suppose if anyone is trying to post anything, and then who are all available in that particular network, and then everyone can see. Okay, and then so therefore the information is passing from one user to rest all users connected with that network is also possible. Okay, and then so that is called as, and then so yeah, maybe a social network communication, and then who are all involved in that particular network, and then everyone can see the concerned information if it is available public, and then otherwise, and then so if you are trying to connect with your friends, and then if you want to transfer anything to your friends, and then so that should also be possible. That is a part of the network group, and then okay, and then so then like that, and then the worldwide, and then there are lots of users, and then all those users are connected in some fashion. Then okay, so we may be one of this particular point, and then I think all these are okay, so visible, it's a very small dot, and then okay, so that one specifies one single user. There may be a connectivity from one user to another user. So if any one person starts to tweet, and then what will happen? And then so who are all available in that friends group, and then everyone can see. Or somewhere sometimes it may be a public tweet, and then so everyone is going to receive it, and then so therefore, and then we are trying to pass the information from one user to another user automatically. Okay, those users are called as vertices here. Okay, according to our graph mechanism, those users are vertices, and then okay, the information flow from one to another, that is done through some connection. Okay, so that connectivity we can call it as edges. Okay, and then so then you may decide it, and then whether there may be any communication or not, and then so we are always not going to communicate at all time. Instead of that, and then there should be okay some time interval to do all such things, and then so it may be either sometimes we may tweet, and then sometimes we may not tweet, and then okay, and then so this is also one of the diagram which represents okay, the graph, and then for example we have different users. Okay, and then so this is user one, user two. Then if anyone started to tweet, okay, and then so and then there may be some mentions, and then any one of the user can post tweet, and then that could be use. Okay, so that could be used by okay, if are you used to from some one source. Okay, any one of the source, and then that may contain any links or some other retweet could also be passed, and then you may get a reply also. That should also be in the form of a tweet, and then sometimes, and then hashtag should also be possible. Okay, and then so like that, and then there should be so many possible ways. Okay, and then so and then users are connected here. These are the major vertices according to our graph, and then okay, and then so and then tweet is also another component, another vertex, and then the communication here is any one of the post. Okay, just take only these two component alone. So user is one of the vertex, one of the component, and similarly tweet is another one of the component. And then what you are trying to do, and then you are going to post something to the something as a tweet, and then okay, similarly just to see here, and then this tweet okay, so mentions some other users. Okay, and then so there should be some connectivity. Okay, just see here, then all these comes under like a directed graphs, and then so then these tweets can make use of some sources, then these tweet some contains some links. Okay, and similarly it may retweet okay something, and then one tweet may reply to another tweet. Okay, like that, and then so there should be so many components. All these are connected in fashion, and then there should be for developing the communities. Okay, as well as and then so how the topics become hot, and then all these things, and then so you may finally compute in terms of performances. Okay, which one could be the best tweet, and then that you can find it out at the as the outcome. Okay, and then similarly how information is flowed from one to another, and then okay, all these are certain application which are relevant to social networks. Then another one social network which is a Facebook. Okay, just see here, so many friends are there, Okay, and then so if any one person is going to, okay, post any of the messages, or they may listen some musics. Okay, and then so and then all these circles are vertices here. Okay, according to our graph component, all these are, okay, so vertices. And then, okay, these lines specifies, okay, edges. Okay, and then so he may have a friend with another user. He likes some posts, or he likes some other, okay, tools or kitchen things, etc. And then so he may cook something, okay, he may watch something, and then he may send a friend request to another user, like that. And then so all those components are integrated together. And then, okay, then there should be a communication from one to another in such case. And then this is the best example for undirected graph. And then Facebook is the best example for undirected graph. And then, okay, then using graphs, and then you may suggest and then mutual friends, and then it shows the list of following pages, okay, followers, friends, contacts list, and then everything, and then you can see. So this is another kind of application. Mm. Then the next application is about transportation. Okay, and then just to see the roadmap. Okay, so vertices are intersections here. Then in case of edges, there should be a road segments, and then, okay, and then so these are the road segments, and then these are vertices, and then maybe from one station to another station, maybe bus station or railway station, anything, and then those are what happened, and then vertices. And then the connectivity road is called as an edge here. And then, okay, always, and then the information flow from one to another. There is a generalized concept. In case of transportation network, what happened, the bus starts from one station to another station. It picks, okay, passengers, and then drops at another station. Okay, and then so this is the best example for it. And then suppose sometimes, and then so it may flows in different directions. And then, okay, one bus starts from here, and then it goes to the next station, and then it may comes this direction. Similarly, it goes away, this direction. Then once again, and then it may comes into the same direction, or it may goes some other directions. And then, okay, so that depends on what could be the route map, and then that could be followed. And then, okay, similarly Google Maps are there, and then so that always shows then which could be the best route between two locations. And then, for example, we are giving the source, okay, and then so where you have to start, and then where do you want to go, okay, and then so for example from Vellore to Coimbatore, and then if you want to see, and then what are the possible ways. And then, okay, if it starts from here, the user is going to start from here, okay, that should be the starting location. They wants to go to some other location, okay, and that should be the destination location. And then there are so many possible ways. And then so you may come through your different stations, and then among that, and then which could be the optimized or shortest path. And then, okay, so depends on which pathway you are trying to use. And then, okay, which traffic, and then you are going to consider sometimes. And then some kind of road is always busy. In such case, and then you are going to omit that path, and then you may take an alternate path over here. Okay, so there should be multiple paths over here. And then if one route is always busy means, and then you may take an alternate way. Okay, and then so such kind of transportation network, okay, reflect our graphs. Okay, and then so this is for used to for studying traffic patterns, traffic light timings, then other aspects of your transportation. Okay, and then so this is another example of graph application. Mm. Then we may have utility graphs. Then so how much you have utilized. Then for example, in case of internet, and then you may have a utilization chart. And then so where it starts from, where it kind of goes, and then how much you have utilized. And then, okay, maybe water resources, and then if you want to plan it. And then so, okay, which other cities are connected, and then, okay, from where to where, and then the supply goes. And then so, okay, finally how much could be utilized for that particular station. And then all those things, and then so you may take it. And then so you may analyze properties of these graphs. And then so that should be very very important. And then, okay, even in case of any failure. Okay, so one connectivity goes off, and then you may use some other alternate path for it. And then, okay, and then sometimes you should also minimize the cost to build such kind of infrastructure. And then one water plant is here at one particular location, another plant is in that particular location. Suppose, and then so if this plant, and then you are trying to use it to supply for, okay, the whole cities. Okay, and then so it covers, and then so certain regions. Okay, and then so then if this plant is failed, and then, okay, if you are trying to make use of another plant to supply, okay, the water, and then which one could be the feasible one. Okay, just assume it, and then there are lots of water supplies. Okay, water supply plants are there, and then, okay, among that, and then which one could be the feasible one, or, okay, which one will be will have the minimized cost to supply the complete coverage area. Okay, those things of utility graphs, and then you may use, and then this should also be applicable for power grid machines, even internet, and then, okay, are the best examples of our utility graphs. Mhm. Then we have another example, like document link graphs. Then, mm. So we have uh, the documents which are stored in different servers within a web itself, and then we just assume that, and then this is a server. Okay, and then all those documents are stored here. Okay, within a particular server, and then, okay, all these circles specifies some kind of servers, and then which holds all our documents. And then sometimes from one server to another server, and then you are trying to upload the document, and then, okay, one to another, and then you are trying to store it. And then sometimes, and then the document is available here itself, then you are trying to download it, and then, okay, to another server. Or if any of the user requests, okay, and then so you are trying to download the document. Or sometimes, and then if you require any of the new document to be posted, and then that comes under uplink. Okay, and then so like that, and then so from one server to another server, or user to, okay, different servers, and then you may have a connectivity. Okay, and then so you are trying to access a document from one to another, that comes under your document link graphs. And then, okay, and then so it is going to have a list of documents, and then which are the documents are available under, okay, which location. That location specifies a server address. It may be available anywhere in the web, and then the server address should be located. Okay, and then from there, and then you are trying to access the document, and then, okay, in between you may have some other servers, and then, okay, there should be a link. Okay, and then so from where to where, and then you are trying to collect the information. Okay, and then so that should be uh, given by your directed graphs. Okay, always. What happened? Yes.
Sorry, ma'am. Sorry for the
Ah,
disturbance. Someone got their mute unmuted.
okay, okay. Mm, mm, yes. Mm. Okay, so from one to another, and then we are trying to access some kind of documents, and then which may be available anywhere in the web, and then, okay, that always specifies your directed edge alone. And then so that's why, and then so the arrows are mentioned from where to where, and then you are trying to access it. And then, okay, it may also reflect some kind of trees. Okay, and then so just to see the direction, so this is a source, and then from here we are trying to, okay, so access at two different location once again, and then the same document is going to given to some more users, and then like this, and then so it keeps on goes, then finally it goes to the concerned or requested user. Okay, like this, and then so you may have level 1 graph, level 2 graph, etc. Okay, and then so those document has to be mentioned under this document link graphs. And then Okay, from where to where it goes, and then always it can make use of directed alone, and then sometimes, and then you may also have hyperlinks. Okay, while you are clicking any one hyperlink, and then it goes to some other page. Okay, this also be an example for hyperlinking, and then okay, so I am here, I am clicking the concerned hyperlink, it goes to this particular server. Once again, if I am going to click anything, it may goes to or redirected to okay somewhere else, and then similarly it keeps on going where the actual information is. Okay, and then so once, and then if you got an actual information, it stops, and then it won't go further, and then like this, and then so it starts to okay starts from one server to okay keeps on referring, and then multiple servers, and then like this, and then so the link goes, and then that kind of links, and then comes under document link graph, and then so this is for analyzing relevance of web pages. Similarly, best sources of information, where is it? And then that you can easily analyze with the help of document graph. Similarly, good link sites has to be okay, given by document link graph. And then, so that is an another kind of application of a graph. So far, any doubts?
Ma'am, no, ma'am.
Okay. Okay. So another application is protein to protein interaction graphs. There. So here, one protein, we can represent it as an vertex. Similarly, another protein should also be an vertex, and then there should be a connectivity from one to another. Okay, that is called as an edge. Okay, if you have any edge from one protein to another protein, so it means that there is some interaction between one protein to another protein. It means that you are going to carry okay, some function. Okay, it may be a biological function in that particular cell. And then, so this diagram says, and then there are so many cells, and then C1, C2, okay, like 12 are there, and then, okay, and then so it may have positioned in different places. Okay, so these are the cells, and then all these colors, and then so circle specifies cells, and then we may have okay an interaction between one to another, and then so that specifies these edges. Okay, and then so it passes some information from one to another, and then all these links or edges have an interaction, and then there should be some interaction between one protein to another protein, and then that says about your protein to protein interaction graph. And then okay, and then so these kinds of graphs can be used for studying molecular pathways, and then okay, and then within a chain of molecular interaction on the cellular processing, so where to where, and then it happens, and then what is to be done, and then okay what kind of interaction is going on, and then those things can be easily measured with the help of this protein to protein interaction graphs. And then okay, so in case of humans, we may have 120K proteins. Okay, therefore lots of interaction can be happened, and then okay, so in order to measure that, and then it will be somewhat very very difficult, and then okay, since and then it is in terms of millions. Mm. So those things can be easily represented with the help of graphs. This is one kind of application. Then another application is network packet traffic graphs. Then so already we said about, and then graph is also called as networks. Network consists of so many nodes, and then those are connected with okay some connection wires or cables. Okay, from one node to another node, and then there should be some connectivity through either physical wire, or it may be an virtual connection, physical connection, or some kind of virtual connection you may have. And then what could be this symbol? Anyone knows? Yes, what the symbol represents under networking terminology?
Ma'am, is it a router?
Yes, yes, good.
Thank
It's a
you, ma'am.
router. Mm. So there are so many routers. all these routers are connected together. Then, for example, just to see here, there are four different pathways. Okay, and then there are four routes which are available within the router itself, and then it can pass an information through four different outlets. There's a meaning here, and then so just see here similarly one more router, and then these two are connected together. Then therefore, and then there should be a packet flow from one router to another router, like that, and then it keeps on going with the throughout the network, and then just consider this is a whole network, so only this one is magnified, and then so so the packet transmission will be happen from one router to another router, like this, and then so it should also be happen in this direction, and then sometimes, and then there may not be any communication at that time, and then so these pathway will be empty. Then just see here, and then so this is the magnified portion of our connection, and then lots of packets are going through this way, and then there should be four outlets, just see here, and then so, and then in that case, and then if anything comes through this, and then it may goes out this, and then sometimes, and then so some other communication will also be happen through this direction, then this may be the incoming way, and then it may be the outgoing way, and then like this packet flow is from one to another, and then that should also be reflected with the help of our graphs, and then so this is called as a packet traffic, and then so traffic specifies, and then it keeps on going, and then so many packets within a common path, and then how many number of packets to be transferred, that we are trying to measure it, and then and then so that comes under network packet traffic, and then even these graphs are used for analyzing the network security purpose, and then similarly in case of any worms are spreading, that you can easily analyze, and then tracking a criminal or non-criminal activity, that you can easily find it out, and then how much data flow is there, and then if there is any link goes off or on, and then those things, and then so you can easily measure with the help of these graphs. So that is one kind of application. Mm. Then next one, next application is scene graphs, and then so it is mainly applicable for graphics and computer games, and then just see here, there are so many components under the particular computer games. And then so there may be a motorcycle, and then there may be a hat, and then so there is some animal sitting over here, and then and then there is a seat, and then so like that, and then different components are available. And then so all those things, and then represent either a logical or a spatial relationship among the object. That comes under a C, and then so we have so many objects. What are the objects here? Maybe a motorcycle, then seat, then hat, and then so this animal, and then so dog, and then so all those are components, and then those components will be treated as objects here. And then so there should be an relationship between one to another, and then the hat is on the animal, and then similarly so it is sitting on the seat, and then so mm, mm, like that, and then so we may represent a relationship between one object to another object, and then and then so just see here, there is a face, and then the hat is on the dog, and then dog is on the motorcycle, and then motorcycle has handle, then similarly motorcycle has seat. The seat is on the motorcycle, and then so like that, and then you may have a flow graph, and then so all these circle represents vertices. And the major components here are, that is, and then the blue color objects specifies the components. And then there what should be the relationship that is mentioned over this flow. All these red color says the relationship. All the blue colors are objects, and then red color specifies the relationship between those objects, and then it means that hat is on the dog. Then similarly, dog is on the motorcycle. Similarly, so motorcycle has handle. Similarly, motorcycle has seat. This seat is on motorcycle. Like that, and then the connectivity should also be mentioned. So what type of graph is this? What type of graph is this? Directed or undirected? Is it a
Ma'am, directed graph, cyclic graph, ma'am. Directed cyclic graph.
yes, directed cyclic graph. Okay, we can say cyclic graph also. And then so, okay, if there is any direction mentioned from only one way is possible, then you can mention it with the help of this arrow mark, and then that is called as a directed graph. Okay, and then so, then this is an best example for scene graphs. Okay, so in case of scene graph, we have so many objects. From one object to another object, we have some interaction. That those relationships should be specified with the help of the edges. Okay, one best example is this image. For all kinds of computer games are comes under, you can say it as an example for scene graphs. Mhm. Then the next one is finite element meshes. Then this is also another kind of application. And then, okay, then we have so many elements. Then, for example, simulation systems are available. Mhm. Even network simulation systems which are available. So, what kind of network is this? What kind of topology is followed here?
Mesh topology, ma'am.
Yes. Okay. So it's a mesh topology. Then it means that almost and then all the nodes are connected with all the rest of the nodes. Then so we can have maximum connectivity, maximum number of connectivity. How much you could have if you have n number of vertices at the maximum? How many number of edges?
Ma'am, n minus one edges.
N minus 1 edges. In case of mesh topology,
Two n edges, two n minus one edges.
2 n.
I'm not sure of it.
Can we say n into n? N into n at the maximum. Okay, so number of edges you may have. Okay, and then so, for example, if you have only 4 nodes alone, just consider only this circle alone, and then so it means, and then so this square alone. There are 4 different nodes, and then if you want to connect all those nodes with all the rest of the nodes, how many edges you require? Consider only these 4 nodes alone. Okay, so at present I may have a connectivity from this one to this one. Similarly, this is to this one. Then again from this third node to fourth one, from fourth to first one. Okay, so now what are the connection we may have? Its corresponding neighbors are these two, but one more node is also there, and then so you may have a connectivity like this. Okay, and then so you may have one more connectivity like this. So similar to that, and then okay, you may have the second node. Just take a second node. These two are already connected. Then we don't have a connectivity from this one to this fourth node, and then okay, so you may have one more connection like here. If it is an undirected graph, at the maximum, how many number of edges are required? Do you understand my question? The number of vertices here are 4. The number of nodes are 4. Okay. I want to connect or make a connection, or I want to communicate it to all the rest of the nodes. So how many number of connections you require if you have undirected graph?
6, ma'am.
4 means, how do you calculate? What is the generalized formula in case of n nodes?
Is it n plus 2, ma'am?
No. If it is 4, and then you may have 6 edges. Okay. If it is of n nodes, What is the generalized formula? So just assume that, and then if you have 5, 5 means, and then how many?
So 2n minus 1 or 2n minus 2, ma'am?
Mm. What is the generalized formula? Yes. If you have n number of nodes, what could be the maximum number of connection if it is of undirected graph? That is the question.
n into n, ma'am.
N into
N.
n. N into n means in case of 4, are you getting n into n? 4 into 4, 16?
Yes, ma'am.
Yes? No, you said 6. I said it is undirected graph. Yeah, take your notebook and calculate it and tell me. For example, you start from a small number. So n value is 3. What could be the maximum number of connections? N is 3.
For 3, it is 3
Hmm.
connections, ma'am.
3 means?
Only three edges will be there.
Okay. Only 3 edges is there. In case of 4?
We have 6 edges, ma'am.
6 edges. In case of 5?
It's 10 edges, ma'am.
10. Then in case of n, how many edges? What is the generalized formula for it?
Ma'am, n into n minus 1 divided by 2.
Yes. Okay. So n into n minus 1 divided by 2. If it is a directed graph, what could be? What should be the generalized formula?
And n into n minus 1. Because
Yes.
for undirected, we'll have 2 count for, ma'am. So
Yes.
divided by 2 will be eliminated.
Okay. Very good. And then so there should be 2 parts and then so therefore by 2 automatically goes off and then the answer is n into n minus 1. Okay. And then so like this in case of meshes and then what could be the maximum number of connectivity which is applicable for here? All the nodes are connected to almost all the rest of the nodes. Okay, so that is a generalized comment on mesh networks. And then, okay, therefore, the maximum number of paths are available. Okay, and then so since and then it should be a fastest communication if you have a mesh network. Then the flow will be okay. The information flow will be faster. Okay, and then sure. So we can also say that, and then so it has almost, and then the connection transmission accuracy will also be higher. Okay, so therefore, if this path is not available, then you may take an alternate path, and then since almost and then all the directions, and then you may be connected, and then okay, and then so then similarly in case of finite elements, and then so we have so much of elements, all those are connected in mesh connection, mesh fashion. Okay, and then so therefore, easily you can transfer from one to another, one finite element to another finite element. And then, so in most of the engineerings, and then so we may use simulation systems. And then, so those specifies and then your flow of okay information. Okay, and so in case of our finite elements and then that we can call it as and then air over a car and then so that may be one of the physical system sometimes and then airplane wing, then you may have and then spread of earthquakes through the ground and then okay that should also pass one information from one to another and then okay and then so these are called as your finite elements and then okay so that kind of application also we are using graphs. Then so mesh graphs are suitable for this finite elements. And then, these elements along with connections between adjacent elements that forms a graph, then that is called as finite element mesh. This is the best example for it. And then, so this is a detailed view. All these are nodes, those are connected in some fashion, and then this portion specifies the actual finite element. Okay, and then we are passing the information from one element to another element. It may have here or there, and then so like that, and then we are passing. And then, okay, so here also we are making use of graphs. Then the next application is robot planning. Then, okay, and then just this is just like a base. Okay, from one way you are trying to start, and then you may pass on to, okay, what are the possible ways and then which are available. Okay, what are the possible transition it has to do, and then so, okay, that is the role of a robot. Then, so therefore it may have, okay, certain vertices as well as edges. Okay, just to say that, and then the robot is going to start from here. Okay, this is one of the vertices, and then this is another vertex, and then it has to move to some other state or some other location. And then, okay, and then so this robot starts to move from this state to another state, and then, okay, this is one kind of transition. Okay, it has to do one transition. So after a transition, the robot moves to some other state. Okay, and then from this state, and then it should take another transition. It may goes to some other state, and then, okay, and then so then similarly it has to take more number of transitions. Okay, suppose if the robot starts to do the continuous motion. Okay, so in that case, and then it moves from one state to another state, and then it keeps on, and then so within a certain region itself, and then it has to do, or it has to take, and then so much of, okay, transitions. Then that kind of robot planning should also should also make use of the graph applications. Okay, so it's mainly for approximating continuous motion. Okay, so that should be in terms of sequence of discrete steps. So from here to there, similarly, you are going to stop for some time, and then after that, one more transition has to be taken place. That may be a different, okay, transition, and then again it stops here. Then it starts from here to next one, or it starts to, okay, this location, or it moves to this state, and then like that, and then it keeps on, okay, continuously moving. Okay, after continuous motion, so finally it reaches its objective, and then, okay, and then so after that, and then you have to stop it, and then sometimes it may go back in the same direction. Okay, so what kind of graph and then you may use? It may be applicable for robot planning. What kind of graph is this? Yes, is it a directed or undirected? Yes, is it directed or undirected in this robot planning? So in this case, it's an undirected. Sometimes it may go in a reverse direction also. Okay, from here to there, as well as, okay, this location to this location, and then both are possible. So it can make use of undirected. Specifically, planning paths for autonomous vehicle can make use of, okay, this kind of undirected graphs. For example, you are going to start one autonomous vehicle. It should automatically start once it reaches the state, and then you have to stop it. Similarly, if it reaches here, and then you have to stop it, and then like that, and then the direction has to be mentioned, and then it can stop at one location itself. And then this should also be suitable for undirected graph application. Mm. Then for neural networks, that's another kind of application for a graph. Okay, this is a simple neural network, and then it consists of so many layers. that you can know. Then all these layer has some set of vertices. Then these vertices which represents neurons. Then similarly, there should be some interaction between one vertex to another vertices. Okay, one vertex to another vertex, and then okay, this interaction you can call it as synapses. Okay, there should be some synapses between one vertex to, that is one neuron to another neuron. All these are neurons. There should be in terms of your different layer wise. If it is a neural network, and then so minimum one input layer and then one output layer, as well as you may have multiple hidden layers. Okay, and then so here only one hidden layer is mentioned. There are okay one there are two vertices or two neurons in the input layer. It means that two neurons, and then you are going to pass it to hidden layer. Then hidden layer has four different neurons. Then similarly, finally, you are going to get only one output neuron. And then okay, how you are trying to get this one single output, that should be from two different neurons of input layer, that is okay transported into or transmitted into your hidden layer. It has to do some processing. Finally, everything should be reflected in the form of an output layer that has only one neuron alone. Here also there is a transmission from one to another. Okay, so that reflects your simple neural networks. Like this, you may have so many hidden layers. Okay, and then so how much you are going to uh, process it internally or in detail. Okay, so that reflects and then deep neural network also. Okay, and then so that could also be one of the okay application of our graph. And then okay, just see here, so all these vertices represents a neuron, all these edges represents okay synapses between them. And then so that should be the interaction among one layer to one vertices to one neuron to another neuron. Okay, and then these networks are used to understand how our brain works, as well as how connection changes when we are trying to learn. Okay, I started to learn. Okay, one neuron will be active, and then that gives different forms of okay outputs. Okay, and then so if I said one thing, and then your brain is capturing all those things, and then okay, so that will not store it in the same form. Okay, instead of that, and then so that has your different okay forms of information which could be accessed internally. Okay, so therefore that may have or that may goes to different neurons. You just assume that, and then what you have inferred is okay, so store it in three different neurons. Then again, similar to that, and then one more information you are going to hear it through this neuron. Okay, that will also reflect in the form of three. Okay, sometimes and then it may have some mixture. Okay, so maybe this neuron inference as well as this particular neuron inference combines together, and then that forms okay or that will do some kind of synapses here. Okay, and then so that may also do some kind of processing within this itself. Then finally okay that will be interpreted here. Okay, that goes to the output stage, and then okay like that, and then so the rest of the neurons will also do some kind of processing all together. Okay, all the results together, and then that will be interpreted at the output layer. Okay, and then so what the overall interference, we have so many neurons, and then there should be some communication from one neuron to another neuron. Okay, so that will also do some processing. After processing once again, and then that should also be communicated to okay your output neurons. Okay, so collectively all together that comes under the output neuron. Okay, and then so it is compared with our brain network. Okay, and then so in case of our human brain, 1011 neurons. Then it may have closer to 1015 synapses. Then there should be an interaction that is to be transmitted from okay these set of 1011 neurons. As a best example for our neural network applications. Then next one, the graphs in quantum field theory. Then Even quantum field theory can make use of our graphs. And then, okay, so we'll have different states, and then those states of quantum system will be represented in terms of vertices. Similarly, the transition from, okay, so one quantum state to another quantum state, and then we can call it as edges. Okay, and then so then that is reflected in this diagram. And then so these are the different quantum states, and then q1, q2, q3, q4, q5, and then, okay, and then so there is a transition from one to another. And then what kind of graph is this? What kind of graph is this?
Directed graph.
Directed graph. And then so if you have any arrows, automatically it says, and then it is a directed graph. Therefore, the information flow is in that direction alone. Okay, just see here, from here to there alone, and the information is flowed. Okay, and then so these quantum graphs can be used to analyze your path integrals, as well as you can do some summation, okay, under this path integrals, and then that will generate a quantum amplitude. And then, okay, and then so those are with respect to quantum field. Mm. Then yeah, coming to our field, and then so it's a semantic networks. Mm. Okay, so here we have words. Here we have words or concepts, and then so those are also there. And then while you are going for any semantic searching, okay, what that is going to do, so we are simply passing some words or maybe sometimes, and then concepts, and then you are going to give it. And then so what are the relevant things, and then so that should be retrieved from the server. Okay, maybe if I am trying to search a word graph, okay, so what are the relevant to this particular word, everything will be written by the semantic web search engine. Okay, and then so it is based on the meaning, and then so we are trying to do. And then, okay, so based on that, and then all the words which you are trying to search, okay, words or concepts, and then those we can say it as vertices. Okay, just to see this example. And then, okay, so which are the words and then you are using here? What are all vertices here? Vertices in the semantic network.
Mammals, deer, animal,
Yes.
whale,
Mammals, bear, animal, fish, water, whale.
whale,
Yes.
vertebra, cat,
Vertebra,
and fur.
cat, and fur. Okay. So all these are the words and then which we are going to use it. And then, okay. And then so these words and then we can call it as vertices according to our graph. And then there should be some relationship. Okay. You are trying to maintain between those two words or vertices. Okay, so in case of a mammal, we can say all animals. Okay, mammal is an animal. So what should be the relationship? Mammal is an animal as the relationship. Animal and mammal are simply a words. Okay, so what we are trying to relate it. Okay, and then so that comes under a relationship that is maintained by the concerned ages. So mammal is an animal. Similarly, bear is a mammal. Okay, bear and a mammal are different words. Okay, are vertices. Okay, so how we are going to make a relationship? So bear is a mammal. Okay, is by using is a keyword, and then we are trying to make a relationship. So that is done through which one? This arrow. Okay, so this kind of graphs are which type? Under which category? Is it a directed or undirected? According to this diagram, is it a directed or undirected graph?
It's a directed one, ma'am.
Directed one. Okay, we can always say bear is a mammal. Mammal is not a bear. Okay, and then so only this direction is applicable. Similarly, whale is a mammal, and then similarly, whale lives in water. Okay, so water and whale are two different words or vertices. Okay, so if you want to make a relationship between these two words, and then we are trying to use the edge. Okay, so this edge says the relationship. What is the relationship here? Lives in. So whale lives in water. Similarly, water, okay, can we say water lives in fish? So it is not applicable. So that's why the direction is mentioned. The fish lives in water. Okay, similarly, fish is an animal. Okay, so based on the relationship, you are trying to make an arrow. Okay, so this is the best example for a semantic network. So we have so many words as well as concepts, and then so from one word to another word or one concept to another word concept, and then we are trying to make a relationship through semantic networks. Okay, in order to represent such kind of semantic networks, we are making use of graphs. That's the conclusion here. So these graphs are used in various model how human organize, okay, their knowledge as well as how machines might simulate within the organization, and then so that you can reflect it. And then, okay, this is another kind of application. Then graphs in epidemiology, and then so here also we have so much of infectious diseases, and then so okay, and then so we have every individual, and then so all those individual may be one kind of users and then our person. Then you may represent a directed edges. Okay, this will also be the best example for directed graphs. And then, so always you have to specify the directed edges. Okay, so there should be a transfer of an infectious disease from one individual to another individual, like this alone, and then so okay, and then so there is one individual, then this is another individual, okay, and then always, and then there is a transmission from one individual to another individual if it is an infection, okay, or infectious disease, and then so that represents epidemiology. And then so this is for this can also make use of graphs, and then it is for analyzing analyzing most of the component, and then how the spreading has happened, and then how to control it, and then that decision we can handle with the help of epidemiology graph. Okay, and then so I forget to draw the graph for it. And then, then similarly graphs in compilers, then so this is also our computer science field. Then specifically graphs are also used in compilers, and then so okay, we can have so much of data flow analysis, and then so we have so many layers within that itself, and then so what should be the first step, and then what should be the second step, you have to take it, and then okay, and then so always, and then what kind of analysis you are going to do in under uh, compilers analysis you have to do. What is the analysis process? First step in the compiler phases, which is the first analysis phase? Which one does the first analysis? Which is the first phase in a compiler? Lexical analysis. Okay, that is the first phase. Okay, after that, and then we are going for syntax analysis. Okay, so in the lexical analysis, what we are trying to do, each and every token has to be separated, and then okay, what is the overall process of a compiler? It will do a translation process. Okay, and then so the user has written the application programming that has to be translated into the machine level, okay, lower language, low level language, and then you have to translate it, and then okay, and then so in order to do that, and then that should be coming under different phases. Okay, first you have to start from lexical analysis, next, and then syntax analysis, okay, that and all, and then you have to do then yeah, after that, and then syntax analysis, next you can go for semantic, Okay, like that, and then it keeps on going. Then next intermediate code generation, then code generator, like that, and then it keeps on going. And then so this is one phase. From this phase, after completion, we are trying to, okay, transfer the information or output from lexical analysis to syntax analysis. Okay, so this is a transmission flow. This could be one kind of vertices, and then this should be the another vertices. This vertex specifies all the lexical analysis process. Once completed, the output is going to be passed it to your syntax analysis phase. Then, okay, and then like that, and then the compiler should also make use of graphs. Okay, and then how the data flow can be happened. And then, okay, and then that comes under data flow analysis. Similarly, register allocation will also be done, and then, okay, at each and every level, and then we are making use of some storage. Then, okay, and then so from one storage to another storage, and then what you are trying to pass, and then or how you are going to trying to retrieve it from the storage. And then either you need to store, or sometimes and then from the memory you are trying to access it, and then that will also have some data flow. And then so those things should also be mentioned in terms of graphs. And then, okay, always where the flow is there, then automatically graph involves. That is the overall idea here. And then you may have some specialized compilers, okay, that will also do query optimization. And then so what are the steps, and then you can minimize within this. Okay, and then that should comes under optimization process. And then something is not necessary, that you may neglect it. And then, okay, and then something, and then you can do it in a parallel form, that should also be applicable. That will minimize the timings. And then so even based on that case, and then you may do the optimization process. Then, okay, that comes under graphs in compiler applications. Yeah, next, constraint graphs is another kind of application. This is used for representing constraint among different items. Okay, we'll have various items. From one item to another item, we are making some, okay, representation or relationships. Okay, and then for example, we have a GSM network, okay, for a cell phones, and then mobile phones, and then we are making use of it. And then, okay, so it consists of so many collection of overlapping cells. And then we have one cell here, another cell, then simultaneously, okay, so multiple calls comes over here. Okay, and then and then that should be reflected with the help of this constraint graph. Then similarly, any pair of cells that wants to overlap, and then that should be must operate in a different frequencies. And then, okay, and then if you have a common frequency, then that could be fine. Overall, under that particular frequency, everyone is going to hear the, okay, voice message or voice calls. And then they will receive the intended messages. And then maybe you may have a particular destination or receiver alone. Okay, they can alone open the exact message. And then, okay, for example, within the app, there are lots of communication is going on. And then, for example, I am speaking here within my area, no one is there, therefore, and then there should not be any noise over here. And then if multiple persons are talking simultaneously or parallelly, what will happen? Okay, everyone is going to hear something, and then we are not able to get the exact messages. Okay, so it's all overlapped, and then we may hear in terms of noises. Okay, and then that's the difference. And then okay, if it is under a particular frequency without any noise, and then we are going to, okay, hear the exact messages. Okay, suppose, and then if there is any overlapping, and then based on the, okay, frequency, and then we are trying to segregate it. And then, okay, and then the best example here is, and then all our cellular phones. And then if you are under, okay, the maybe one particular vendor or subscriber, okay, so what will happen, what will have it here, and then we have a common tower. Okay, so that we can technically call it as base station. That base station hears all the communication within that particular area. Okay, and then so there are lots of communication happen within that particular area. So everything is heard, okay, or listened by the concerned mobile station. Okay, so it means base station. Okay, and then and then what it is going to do, and then if it is intended to that particular connected mobile cells. Only those things alone will be retrieved, and then that should be passed to the concerned mobile user. Rest all things are neglected. And then okay, and then so this is about a constraint among items, and then there may be some kind of overlapping is also there, and then okay, we may keep on listening so many things, and then what is required for us, and only that kind alone will be taken out. Then that is to be okay. Rest of the things should be neglected, and then okay, and then so that is the best example for constraint graphs. Then this is another kind of constraint graphs. Mm, yeah. So what are the productions, and then you are going to do products. Okay, A and B is here. First you need to check, and then so these two are non-zero. If it is non-zero, then you may go to the next one. So final objective here is A into B. That should be the final output we are trying to get. Okay, and then then first you need to check, is there any constraint here? Okay, in case if it is zero, then your final output leads to zero alone. Okay, therefore no need to do for such kind of processing. Okay, so no need to calculate the product, and then that is not necessary. That you are trying to decide based on the constraint, and then what is required, only that alone, and then you are trying to capture it. And then initially if it is zero, no need to do any such kind of functions. And then, okay, and then then if it is non-zero, then alone, and then you are going for next step, and then okay, and then the final output should also be okay checked, and then that is with also a constraint graph, and then okay, and then so on. So after multiplication also you should not get zero, otherwise, and then the product will also leads to zero alone. Okay, that is not necessary. Therefore, and then non-zero bit edges, and then so you need to calculate it, and then okay, this is an example of another kind of constraint graph. Okay, then the last application, we have a dependence graph. Okay, sometimes, and then graphs are used to represent dependencies. Okay, and then so for example, there is an entry here. You need to check. Okay, x is 5, y is 5. These are the initialization, and then okay, x is 5, y is 5, and a is 1. Suppose if a is less than 5, then alone, and then you have to do certain process. If the constraint reaches, then what will happen? And then you are going to stop. Okay, and then so you have to finalize the concerned value, and then so that kind of dependency you are trying to do. Then while you are finalizing the use of x, okay, and then that depends on the initial value. Okay, and then similarly, okay, this state, and then is dependent on another some other states, and then okay, and then so that kind of dependencies are represented with the help of dependence graph, and then okay. So these are used in large kind of projects, and then okay, specifically what the component rely on another component. Similarly, it is used to minimize the total time or cost for completion. Okay, for that, and then we are making use of this dependence graph, and then how much time is required, and then if you want to complete a particular project, okay, that you can decide it, and then so there are lots of teams are there. If one team is completed, then alone that goes to the next team. Then if sometimes, and then these two teams can act parallelly. Okay, in such case, and then the cost will be reduced. Our total time could be reduced, and then okay, and then so that dependency has to be taken care. And then suppose if it is completely dependent on this particular team, they have to wait for a certain period of time, and then till that, and then these team members are jobless. Okay, and then okay, that dependency we are trying to do. And then based on this dependence graph, and then you may do the optimization process. Okay, and then so that is done with the help of these graphs, and then so these are the different kinds of applications that comes under graphs, and then till this my side is over. Any queries over here?
Professors, if you have any queries, you can ask Usha Devi ma'am. And I think they don't have any queries, but we really enjoyed your session, ma'am. Like we were able to know the vast applications of graph in various fields. It's
Yeah.
really such an useful session, ma'am. Thank you so much for giving us such a good session, ma'am.
Thank you, ma'am. And then
Thank
so.
you.
I think these are apart from our syllabus, and then so. But I try to relate with our engineering fields.
Yes, ma'am. Actually,
Mm.
that was really good, ma'am. Thank you so
Mm.
much for the session once again, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Specifically, thanks for the audience, and then so for patient listening.
Thank
Then
you.
thanks to your team, and then so for
Okay, ma'am. Thank you, ma'am.
arranging. Yeah.
Okay,
Thank
ma'am.
you.
Okay, ma'am. I think they don't have any queries, ma'am.
Shall we wind up, ma'am?
Yeah, we can wind up, ma'am.
Thank you all.
Thank you, ma'am.